Welcome everyone. Thank you for joining us today for the second presentation of our April webinar series. My name is Adam Galata. I'm the Marketing Manager for the EMEA region at Monolithic Power Systems. Today I'm joined by Mario Villeit, our Senior Field Applications Engineer for Southeast Germany and Austria. He'll be presenting solutions for powering Intel and AMD SoCs. Before we get started, if you have any questions during the presentation, please type them into the question box in your Zoom control panel. I'll bring them up at the end of the presentation during our Q&A session. All of our webinars are available for on-demand streaming on monolithicpower.com. Today's webinar will be added in a day or two, along with the presentation materials. Now let's get started with the presentation, and I'll turn it over to Mario.
Thank you, Adam. So good morning and welcome to our Embedded Computing webinar. My name is Mario Villeit. I'm working since 2013, so almost more than 7 years as a field application engineer for MPS. I'm located in Germany, close to Munich, and cover all our products. In the next 25 minutes, I will give you an introduction to our power solutions for x86-based SoCs from Intel and AMD. Here is the agenda for today's webinar. First, we will see how our solution for powering Intel and AMD SoCs look like in principle. Then we will have a closer look to the main building blocks, the digital core controller and the corresponding power stages. These are also well known as DrMOS, DrMOS, and we call them IntelliFace. After that, I will give a brief introduction to the design tools we can offer. Before the summary, we will see what parts are required when doing a real Tiger Lake UP3 design. Finally, there is time to ask questions. Our solution to power the dynamic rails of SoCs, I mean those rails who are frequently altered during operation, consists of a digital controller and one or more IntelliFace power stages. Our controller are powered by 3.3 volt, whereas the power stages can operate in a much wider voltage operating range. We will see the details later. The SoC talks to the digital controller through a specific interface. Therefore, we have these different parts. Currently, we support Intel IMVPx 9.1 is currently under development. For the server, we support VR12, 13, 14, and for AMD, we support SVI2. SVI3 is currently also under development. There is also a PM bus interface, which can be used to access the digital controller internal registers for either tuning or debug purposes. When we are going to the tool sessions, we will see further details how the PM bus is used. The output voltage from the SoC is remotely sensed. We use 2 differential amplifiers in the digital controller for that purpose. Our solution allows ceramic-only output designs as well as mixed POSCAP and ceramic designs. The interface between the controller and the power stages consists of a PWM signal to switch either the high side or the low side fed on, or to put the power stage into diode emulation mode to achieve DCM, discontinuous conduction mode operation. The power stage itself reports the instantaneous current and its temperature to the digital controller through the CS, the current sense, and the temp pin. The temp pin is also used to report a power stage fault to the controller. For the other system rails, we have dedicated point-of-load converters. All of them are synchronous buck converter with integrated FETs. Some have pin selector with standard output voltages, and the regulators are targeted for dedicated SoCs and fulfill the corresponding timing requirements. For example, when changing the power state. Other POLs are universal parts with resistor selectable output voltage. These devices have typical input operating voltage from 4.5 to 24 volts. But this is just an excerpt from our portfolio, so we can offer also devices with much lower input voltage range. But these mentioned devices with the NB name, they are for dedicated SoCs, which need also dedicated timing requirements. Now let's have a closer look to the digital controller. Our portfolio consists of controllers which can support between 1 and 3 rails and a fixed amount of phases, up to 12. Those phases can be assigned to the different rails as needed. The implemented control algorithm is based on constant on-time with ripple injection. This algorithm has been patented and allows to reduce the required output capacitance to fulfill the SoC vendor transient specifications. The controller is fully digital and requires a minimum of external devices. All the internal configuration registers can be accessed through PMBus. There are several telemetry functions implemented. Input-output voltage, output current, and temperature measurements are supported in all of our devices. Input current or power measurement require an external device that does the measurement. But quite often a charger is used that automatically determines the current or the power. Some controllers also have a specific amplifier implemented that allows to add an external shunt resistor to measure the input current, but this depends on the controller. There are several protection features implemented too. There is an overcurrent protection. Exactly, it is a configurable per phase valley current limit and a configurable average rail current limit to protect the design. Configurable in this case means you can set either the protection value in amps, but also the protection behavior. So for example, you can retry or latch off if a fault happens or simply ignore the fault. The ignore does not make sense to set it permanently. It sometimes makes sense to set it during debug or bring up sessions. We have over and under voltage protection. This is related to the output voltage. This is also adjustable within certain limits. Over temperature protection speaks for itself. We do automatic voltage positioning, and this is supported by setting a load line digitally according to the SoC vendor specs. Optionally, the controller can add or remove phases in a multi-phase design based on the instantaneous output current and other configurable parameters. For multi-phase designs, there is also a digital current balancing algorithm implemented that can be configured and trimmed. Trimmed in this case means that you can do some imbalancing for thermal reasons. For example, if you have 3 power stages and the middle one becomes too hot, you can spread or distribute the current difference so that the outside power stages get more current and have then the same temperature as the middle one. But this happens quite seldom. Now let's have a closer look to the power stage, which MPS calls IntelliPhase. Indeed, this is a DrMOS or DrMOS where 2 MOSFETs and the corresponding drivers are implemented on a monolithic die. Our power stage portfolio consists of many parts ranging from 12 to 80 amps output current capability and a maximum operating voltage from 12 to 22 volts. We offer them in an MPS proprietary package, but also in common footprint packages. The switching frequency range is from 100 kHz to 3 MHz. The switching frequency, of course, is determined or set by the digital controller. A good compromise between efficiency and transient is a frequency range between 700 and 800 kilohertz. The power stages have built-in zero current detect for diode emulation implementation, fixed peak current limit, OCP, negative current limit, which might be hit at SOE down, over temperature protection, and short circuit protection. So you can see it's very hard to kill such a power stage, but be sure, it's not impossible. Beside the digital controller, these power stages are the key for the easiness and performance of our solution. The main reason is the accurate on-die current measurement. It provides a ±3% accurate current signal for the digital controller. Let's continue with the power stages. The power stages use a monolithic design. This means everything is on a single die. Typical other devices from competitors use multiple chips in a single package. Our technology allows us to reduce propagation delays as well as dead time reduction. This is done, and you should see it in the picture below, by having many single drivers that drive parts of each MOSFET. Each MOSFET consists of many, let's say, single, simple, small MOSFET cells, and they are all set parallel. And some of them have a dedicated driver. And the big advantage of this is that we can have a short dead time and short delay times. And the advantage of the short dead time is that it reduces the power loss, because the body diode of the low side FET does almost not carry any current when switching from high to the low side FET. And the diode, if it does not conduct any current, there is no current or charge that has to be discharged, and this improves their efficiency. Having many drivers for parts of a single MOSFET does also allow to switch off parts of the FET. We call it partial FET off, and it allows to increase the light load efficiency a lot as the switching losses are minimized. Another huge advantage of the monolithic design is the ability to measure the current in the MOSFET by using a current mirror technique. So it's a lossless technique that allows to measure the current. All of our DrMOS devices have a current sense pin that sinks and sources a current that is proportional to the real current flowing in the FETs. The current sense accuracy is factory trimmed and almost independent of temperature, voltage, and the inductor parameter. So it is not dependent on the inductance or the ohmic resistance of the inductor. This makes your work much easier, as you don't need to use and always use this specific inductor, which has certain inductance and ohmic resistance. You also don't have to design a temperature compensated RC network across the inductor to create a small inductor current proportional voltage. And this voltage is quite often noise sensitive and critical to design. Our solution instead provides reliable and accurate current measurement, which is not only important for protection purposes, but also for the overall system performance to get most out of your design. One example would be the exact current measurement, where it is important is the Intel Turbo mode. The on-die current measurement is one of the biggest advantages of our solutions, in my opinion. Finally, we use a certain package technology. It's called flip chip. This is in general not a new technology, and many other vendors use this technology too. Unique to MPS are the copper pillars that we grow on the die to solder the die to the lead frame instead of using solder balls. These copper pillars have accurate and reproducible mechanical dimensions, which solder balls don't have, and this allows us low parasitic resistance and inductance. This, on the other hand, reduces the ohmic losses within the package, and due to the reduced inductance, it reduces the switch node ringing. Furthermore, this packaging technology is highly reliable due to these copper pillars. This has been proven when doing several thousand thermal cycles from -40 degrees to +125 degrees during automotive qualification of our parts. Our next topic are design tools. So we provide first reference designs for many popular SoCs from Intel and AMD. If you don't have it, what you're looking for, we will create it for you. You will find MPS also on many reference designs from the SoC vendors. Every IntelliFace datasheet has detailed layout guidelines, and we provide additional presentations for the controller layout. If possible, you should strictly follow the layout guidelines, especially the placement and routing of the power stage input capacitors are quite important. If you are not sure, we will review your schematic and your layout. We can do this simply by email, or we can also set up Zoom or other meetings to do the layout online. Finally, we offer several evaluation boards where you can use the test tool from the corresponding SoC vendor. One example would be the Intel VRT tool to do the load transients and all these validation steps. Controller configuration is necessary to adapt the controller, the settings to your design. Most configuration parameters are dictated by the SoC you're using, and it also depends highly on the input voltage range. MPS does provide the initial configuration based on our experience we made with previous SoCs or customer designs and tests we've done based on our evaluation boards. Quite often, the initial configuration we are providing is also used for mass production at our customers, so no changes have been needed. When doing design validation, it might be anyway necessary to tweak some parameter. Therefore, we have an Excel configuration sheet that has a dedicated section how to tune the design. The output of this Excel file can then be used to configure the digital controller with new parameter. After configuration, you immediately see the results. This speeds up validation time a lot. To access and reconfigure the digital controller, you need a Windows PC running MPS GUI software and a USB to I2C converter from MPS. What you should forget is to put test points or a connector to access the PM bus on your PCB. Now it's time to show a few products. Let's start with a single rail 3-phase controller, which is Intel IMVPx 9 compliant. This controller is used in current Intel reference designs for Elkhart Lake and Tiger Lake. The shown feature list is a copy from the MP 2940A datasheet. It reflects the features discussed already in the previous slide about digital controller. Let's use the shown schematic now to discuss the required external devices, mainly resistors, and what they are for. First, there are a few resistors needed to convert and scale the current signal from the power stage to a voltage signal, which is sensed by the digital controller. Another resistor plus a capacitor, which is not shown here, is needed to scale and average the complete rail current for reporting purposes. You might know that Intel SWIT protocol reads the current back, and this is the reporting feature, but this can also be done through the PM bus, and you will see it in our GUI software. The load line implementation requires a further external resistor, and to measure the input voltage, a resistor divider is needed too. For some other reasons, for example, turbo mode, there is the possibility to let the SoC know what's the actual power consumption of the AC brick power through the digital controller. Therefore, the controller gets a current signal from an external device, mainly from a charger that is proportional to the power of the AC brick. The shown resistor at the PCS pin is for current to voltage conversion and proper scaling. So this is an optional feature, you don't need it, but especially if you're doing kind of laptops where the power is limited by the AC brick, then this is an important feature. Here you see a digital controller example for our AMD. It's an AMD SVI2 compliant 2-rail 5-phase controller. The main features are the one already discussed. You can see that this controller is possible to auto-record the faults that happen. This are stored in the internal memory and can be read out through the PM bus. There are several variants of this 2945 controller. They always have 2 rails, but higher amount of phases. So 5 phases is the smallest one, but it's sufficient for the most embedded designs we have. We also work with AMD on the next generation SVI3 controller. It will be available around mid of this year then. This slide shows now an excerpt from our DrMOS portfolio. You can see a lot of devices, most of them are 22-volt devices. This is the maximum operating voltage shown. The 22-volt devices are ideally suited for wide input voltage range embedded designs, for example, for COM-Express designs. The 16-volt devices are limited to the typical 12-volt plus minus 10% supply designs. Finally, the 12-volt designs or devices are normally for designs with input voltages below 12 volt. One example would be the smart platform, which runs from 5 volt. All our DrMOS devices are based on our flip chip technology. We already discussed the features of this technology. For successful design, it's important to remember to follow our layout guidelines, and that heat dissipation mainly happens through the device pins. Please use thick, ideally 70 micrometer solid ground plane and thermal wires to get the heat out of the DrMOS devices. In general, all pins help to conduct the heat, but not all of them can be connected to large copper areas. So now, as promised in the agenda, we will have a look into our Tiger Lake UP3 reference schematic. In this design, MP2962 controller has been used for VCC in and VCC in auxiliary generation. VCC in is the IMVP9 SWIT rail, and VCC in aux is a 2-bit P-bit, a parallel bit rail with 4 different voltage settings. As you can see, in principle, it looks like the schematic from the datasheet. The only difference is that some resistors are implemented as two resistors in series, because the resistances or the value of the resistance is quite important for proper working of the device. The exact value are calculated in the Excel configuration sheet. We have seen it already in the tool section. If you enter all the design parameter, you also get out the values for the resistors and the capacitors from this design tool. Here you see the power stages for the VC power rail, which is a 43 amp thermal design current spec. We have used a two-phase design with a 22 volt, 30 ampere power stage called MP8694-1. For VCC and AUX, which is much smaller from the thermal design current, which is 14 amps, only a single rail is used with a similar power stage. Important for you is always the amount of external capacities and the output. What you see here are the capacitors needed close to the power supply, not all these decoupling capacitors close to the SoC. So due to our constant on-time technology, which is very fast, and the power stages which can react quite fast, we can limit the amount of external capacitance. You see here in our reference schematic that we use 15 22 microfarad and one 330 microfarad capacitor. This should be enough, but keep in mind that your real used capacitors might have or need some voltage or temperature derating, and you should also consider the aging of the capacitors, that you finally see a much lower capacitance or real capacitance value than what's written in the data sheet. Yeah, this slide shows further rails which we address in the Tiger Lake UP3 design. Okay, just a moment. Yeah, now I'm back. Okay. Here you see the 2941B device. This is a device that can be alternatively used for VCC and AUX. It's a point of load device which can supply up to 28 amps. Excuse me. Then we have dedicated devices for LPDDR4, 4X, and LPDDR5. These devices provide up to 3 rails. One of them is supplied by a buck regulator, the other 2 by an LDO. The beauty of this solution is that it has also implemented the power sequencing inside the chip. So it's a single chip solution for a complete design for SDRAMs. Then we have pin settable devices, the NB690 and 695A. The 690 is an 8 amp device. The 695 is a 3 amp device. So the 690 can put out 5 volt, 5.1 volt, and 3.3 volt, and also has a 100 milliamp LDO inside. The 695A are used here for VNN and V1.05 bypassing. And finally, we have universal regulators where the voltage can be set through external resistors. The 591 is a 3 amp device, and the 691 is a 6-amp device with a peak current of 7.5 volt. Okay, and here is the summary before you can ask your questions. You can see we can offer a complete solution. So it's a one-stop shop, what we are here regarding our AMD and Intel designs. The digital controller eases the design process and the verification. The fast control loop allows reduction of output capacitors to fulfill all the vendor specifications. The high efficiency of the monolithic DrMOS devices with low thermal resistance flip chip packages support space-constrained designs, especially when you look at a smart platform. The accurate DrMOS on-die current sense leads to better overall system performance and much less engineering effort. You don't have to do any inductor DCR sensing and temperature compensation. We have great design support. We provide the initial controller configuration. We have layout guidelines, and we provide schematic and layout review. This reduces the risk and saves the development time. So if you have any questions, you can ask them, or we might have already asked them in the chat forum, but if you have them later, you can drop me an email if you want. So back to Adam.
Thank you, Mario.
Yeah.
Yeah, thanks for that that great presentation. It looks like right now we don't have any questions in the questions box here, so I'm going to just thank everyone for being here. We appreciate you taking part in our webinar series. If you have any other further questions, as Mario said, regarding today's topic, you can email either Mario or myself. My contact information is located in the invitation. Thanks again, and hopefully we'll see you next week, where we continue our webinar series on Tuesday and Wednesday. The details you'll find on monolithicpower.com. Bye for now.
Bye-bye. Thank you.